Do you hear me now?
Yes.
Okay, thank you. I think I talked when I was muted. There is a section here about partial frames. But before that, I want to make some more general comments. We had a week on respaces and frames about 2 weeks ago. And immediately talking about partial frames here does not show what's going on. That is why it's better to explore it a bit more. In a Hilbert space H, we usually talk about an orthonormal basis. Just good many properties can be proved by an orthonormal basis. Let's call it ES with index S. And I here is not necessarily countable. For any Hilbert space, it is true. And the most important property of orthonormal basis is this representation. For every element, we can write F is equal to a coefficient. We know what the coefficient is, times S. And here we have an unconditional convergence of the series to F. Very good, very useful representation. But there are some problems with orthonormal basis. The most important one is probably that when we do a little bit of perturbation, f of ES is given, the function is given. I mean, we change it a little bit. I mean, I call it epsilon, which also can depend on S, and call this function f of S. So ES is given the original one. And you change it a little bit, call it FS. FS fails to be an orthonormal basis in the general setting, not an orthonormal basis anymore. And this is important for application because, for example, in signal processing, in telecommunication, we have noise, which is our epsilon here. We start with something which is good, orthonormal basis, but immediately with a noise, we obtain something which is not orthonormal anymore. That is, just as an explanation why we see such things. That is why a mathematician started to think about other objects such that still we can have such a representation, even unconditional convergence. And it's kind of stable under some perturbation. It means that we have this representation for ES. If we change a little bit ES, then still we have a representation with some coefficient with respect to FS. I don't say for every perturbation, but for some, still it holds. So we have to move from orthonormal basis to something else. And this brings us to the concept of, shoulder bases and then wrist bases and frames. There are several ways that we can define any of these objects. One of them is by operator theory tools. The good thing about this approach is that by looking at the definition, we see what's going on. And but to extract the properties, it takes time, and we have to cook a little bit to obtain the required result. I summarized the way we can use operator theory to make the definition. But I will present some other definitions for risk spaces and for Parseval's, which sound to be different, but they are connected and in fact equivalent. We can go from one way to another. Let's start indeed with an orthonormal basis. You have seen the original definition. They are normalized, orthogonal to each other, and create the space. Here is another way to do it. There is a mapping U from L2 of S to H. And I would like to use ES for the elements of L2. I'm sorry, please let me change these to say F and these to G, not to mistake with E of S here. ES is an orthonormal, canonical orthonormal basis for this. It means that at one point is equal to 1, at all other components is equal to 0. And this is mapped to F of S here. If the map, that's the point that you need to remember. The map U is bijective and an isometry. Short term for this is a unitary map. A unitary map from L2 of S to H. Then it maps an orthonormal basis here to another orthonormal basis there. So in this case, we obtain an orthonormal basis. So I repeat, we have a map from L2 of S to H, bijective and isometric orthonormal. Now we can relax the assumptions that we have. Isometry, we can relax it. Bijective, we can relax it. And we obtain something else. If we relax this, and instead of isometry, we just assume that it's bounded, but it's still bijective. So a map which maps ES to FS, but the map is bijective and bounded, this gives us array spaces. That's a definition using operator theory tools. And in the second step of relaxation, still when we have bijective here, you see that the kernel is 0. In other words, our representation is unique. This representation of F is still unique because the map is bijective. So we keep bounded, but replace bijective by surjective. Just being on 2. What we obtain is a frame. So that is why I said when we look at these 3 objects, orthonormal basis, risk basis, and frame, from operator theory point of view, it's easy to describe. We have a map U, and we relax the conditions, we obtain OB, we obtain risk spaces, we obtain frame. But after that, we need to work a little bit more to say, to obtain equivalent definitions for risk spaces or equivalent definition for frames. Many books start with the other one, which I will mention momentarily. But when we do that, this picture is not available, and we have to obtain it later on. At any rate, we have to start from one of them and do some work to obtain the other definitions. So let me start with the definition of risk spaces.
Sir,
Yes.
when you have bijective and isometry, then your H will be separable.
S is not necessarily countable.
Oh, okay, right.
Okay, it can be in the countable case. Yes, we have a separable Hilbert space, which is, I mean, usually the case in our studies, but in the general setting, that's not the case. Even you need to be careful. In some books, they write Fn, and usually when we write Fn, n is an integer. I can show you books which write Fn, but say that n is not necessarily an integer. Be careful, it's a general net. So, but anyhow, the definition is the same for in all cases. Now, as I said, the second category of definitions which are equivalent to the previous ones, but with this definition, we can get more rapidly the properties that we want. Respaces, I will pass over this rapidly, but still I mention. So f n bigger than or equal to 1 in a separable Hilbert space H is a RIS basis if there are constant A and B bigger than 0 such that the sum of CK FK, the norm in H squared. Some books write a finite number of sums, but even, I mean, an infinite number is okay too. You can go to a limit. So either K from 1 up to M or from 1 to infinity is controlled from above and from below by the norm of the coefficient in L2, sum CK squared. So CK squared. Controlled means you put a constant here, A, and a constant D. The values of the constant A and B are important, in particular in numerical calculation, but if in our calculation they are not, the notation that we use is like this. This is equivalent or asymptotic to the sum of CK squared half, which is, I mean, the same thing as the norm of CK in L2. So they could, of course, for an orthonormal basis, this is the case with A equal to B equal to 1, but we relax a little bit. The relaxation here is seen as the existence of this A and B, which are not necessarily equal to 1. Over there, the relaxation is going from isometry to bounded. These are the same, but to prove they are the same, you need to, I mean, study more about this. In the 1, 2, in the orthonormal basis case, we had this representation. F, the sum of F inner product with Fs times Fs. The difference here is that, so the theorem for the orthonormal basis, for the RIS basis, said let Fn be a RIS basis. That's the most important theorem about RIS spaces in Hilbert spaces. in H. Then there is a sequence, even a unique sequence, Gn n bigger than or equal in H, such that for any f in H, we have the representation f equal to the sum. Some coefficients time fn, but the coefficient here are given by inner product of f with Gn. In the previous case, when we had orthonormal basis, Gn was equal to Fn. In the general setting, no, it's not necessarily the case. And we can say more about Gn. It's called the bi-orthogonal sequence for Fn. Even we can go a bit further and explore some properties. For example, even we have this one. Even Gn is every spaces, which means that we also have f inner product with Fn times Gn when we sum up gives us the function f. I stop here to talk more about these spaces because it's a huge theory. I just wanted to touch the beginning to say what's going on. The good thing about here, the Riemann spaces, is that the representation is unique. The coefficients are uniquely given with respect to Fn and uniquely given with respect to Gn. In other words, if by any method you discover that f is equal to the sum n from 1 to infinity, sum alpha n times Fn, there is no liberty for alpha n. We know that alpha n has to be f inner product with Gn. So the uniqueness which is accompanied for orthonormal bases is saved for Riemann bases too. This is going to be lost in the next step when we study frames. Frames is another step for generalization. The goal for frames is to have a representation like this, but not necessarily a unique representation. F might have even infinitely many representations in terms of Fn. In the language of operative theory, this is translated here. Surjective, not injective, and not injective means that there is a kernel here. And if there is a kernel, many elements can be mapped to 0, which are not 0. Another feature of this is precisely here. We have such representations, but these are not unique. The second way to define a frame is via this definition, which, really not similar to what I gave above operative theory, but at the end of the day, it's equivalent. It's not something different. Definition. A sequence Fn in H is a frame if, as before, there are constant A and B strictly positive, such that the sum k from 1 to infinity inner product of f and fk mod squared is majorized and minorized by the normal f in H squared by some constant. You can put A here and B. Again, you see what's here. This is a map from the space H into L to S, not from L2 to H, from H into L2. Let's map from H to L2, which maps F to the sequence F and Fk. The case component here is in L2. The case component is F inner product with Fk. That's in H. And what you see in the middle here is the norm of this mapping, the norm of this element in L2 squared. So the norm is controlled by the norm of F from above and from below. If, sorry, if A is equal to B equal to 1, you have an isometry, but I consider before that just case A equal to B. This is called, there is a specific name for that, what kind of frame? I apologize, I forgot the
It's a
name.
tight frame, no?
I'm sorry?
Oh, no, it's for one. For one, it's a tight frame.
No, this is tight frame. Thank you. This is tight frame, and if A is equal to B equal to 1, it's called Parseval frame. And in the book, it started precisely from here. Why I mentioned all of this? Because in the previous case, you saw in the risk basis case, we show that Fn is given, Gn exists such that we have this representation. In the case of frames, they show that the operator S equal to T star. What is T? T is the operator I mentioned about this operator T from H to L2, which maps an element into its coefficient in L2. They show that this operator is invertible. And then we have this representation. So the most important representation in the frame theory is this one. S of F is equal to the sum n from 1 to infinity F inner product with Fn times Fn. So the sum we obtain here, n from 1 to infinity F inner product Fn, is not quite equal to F. It's equal to S of F. In the previous case here, either F with Gn times F, or in the orthonormal basis setting here, it gives us F, not S of F. So that's one thing. But the good thing is that this operator is invertible. One thing that we can do is to multiply both sides by S minus 1. So one formula is this: F is equal to sum F Fn S minus 1 Fn. It's very similar to the previous representation. That's one function, that's another function, and we have a representation. Another, instead of multiplying both sides by S minus 1, is to replace F by S minus F in this formula. So it gives us S of S minus F. Fn, and then we see that F is equal to the sum. S is self-adjoint, so S minus 1 is also self-adjoint. These two formulas, this and this one, are very similar to the previous two formulas that we had here for respaces. But in terms of Fn and Gn, now we have in terms of Fn and S minus 1 Fn. So as a representation is a representation for F. So in a sense, we succeeded. We obtained the representation. Two features. First, it's not unique. In other words, it is possible here that we have F equal to sum n from 1 to infinity alpha n Fn, but alpha n not equal to F S minus 1 Fn. We lose the uniqueness of the coefficient. That's not, in many applications, a big deal. As long as we have a representation, it's okay. Second, which is more serious in application, is that S minus 1 is not easy to calculate. Fn is given, so the calculation of S minus 1 is a problem. And we need other, numerical methods to obtain this. That is why, in this case, tight frames and parseval frames become more important, because in the case tight frame, when A is equal to B, S minus 1 is very simple. Is just equal to 1 over A identity. So pretty much here, we obtain what we want. F becomes F equals to the sum n from 1 to infinity. F and S minus 1 is 1 over A. So here is Fn, here is Fn, and 1 over A comes. It's very, very close to what we have to orthonormal basis. And even if we have a parseval basis, a parseval frame, sorry, it becomes the same formula that we had for orthonormal basis. This could be very misleading if you do not pay attention to the fact that the coefficients are not unique. In other words, even in this case, even in the case A equal to B equal to 1, it is possible to have another representation, but alpha n not equal to F inner product Fn. In the book, we just have this one, this representation. And look what happens in the original definition if A is equal to B. Here is the original definition. If A is equal to B equal to 1, the definition becomes, so I repeat the definition here. The definition is case A, B equal to 1. For any F in the space H, norm of F squared is equal to the sum F inner product with Fn squared. That's a definition. In this case, I will prove indeed. I didn't give the proof of the formula in the cut here, but I will prove it. We have this representation, but it is not unique. It will be for the next. In the remaining time, few minutes remaining, I give one example to ensure you that it is possible to have the representation, and indeed many representation. So, example. let H be any Hilbert space. And consider two orthonormal bases for H. One of them we represented by U index S, when S is in S, and orthonormal basis. Another one we represented by V index T, another index T. Again, an orthonormal basis. With each of these, we have a representation which is unique. I mean, F equal to some S in S, F inner product with US U index S. This is unique. Also F with respect to T, F inner product VT and VT, again unique. That's the classical one that we have seen many, many times. Now consider this setting of define, or consider this setting. The set U 1 over root square of 2 US S in S union 1 over root square of 2 VT. You will see the reason for 1 over root 2. So our index set is S union T. So S union T is our index set. And I want to show that this is a Parseval frame. To show the Parseval frame, the definition is like this. I have to study the sum F inner product with all elements square. I write here F, but if I write Fs, it will be mixed with this one. If I write Ft, it will be mixed with this one. I write iota, where iota is in S union T. So if iota is in S, F iota is this element. So F iota is equal to 1 over root 2 US if iota is equal to S, and if iota is equal to T is over 1 over root 2 VT. So what do I obtain? I obtain two sum. This is equal to sum S is in S, F 1 over root 2 US squared, and another T is in T, F 1 over root 2 ET root square. Can extract root 2, it becomes squared. So I have F inner product US squared, another half T in T, F inner product VT mod squared. And we know that each one of this is equal to norm F squared. So I obtain norm F squared in H, because each of them is an orthonormal basis. So from beginning to the end, I have this equal to this. Therefore, I have a Parseval frame. as the collection F iota. Iota is in S union T is a Parseval frame, which two comments. If I remove 1 over root square 2, it's still a tight frame. It's not a Parseval frame. The coefficient A appears. So a normalization is hidden here with root square. And the second is that I show we have a representation. And this was the representation. If A is equal to B equal to 1, that's for the separable case, but in any dimension, F is equal to F inner product with F iota times F iota when iota is in the space. Again, this becomes a triviality here because we know the representation with respect to US and with respect to VT. But if we repeat it here, it becomes F equals to the sum S in S F1 over root square US 1 over root square US, that's half of it, plus T in T F1 root square VT one over root square VT. Can leave it as it is. That's a representation with respect to our elements. But if you want to take 1 over 2 outside, I mean, these two, it becomes a half FUS US plus a half FPT times VT. The sum. I mean, it's not a good idea, but just to show that this is equal to F, because this is F, and half plus a half, it gives us F. But let's stay with this representation. To conclude that, what I wrote here, I believe. Where was I wrote that the coefficients are not unique? Yeah, here it is. We have this representation, but we can have other coefficients. For example, here, if I remove this, then at the same time, I can write this is equal to the sum S times S US 1 over root 2. That's our basic element. And here, F US root 2, that's my coefficient alpha, plus 0. That's another representation, because this part is 0 and the other part is the one we had before for the orthonormal basis. This one. It's kind of trivial, but the goal is not to give an example which is trivial. The goal was to show that it is really possible to have other coefficients. And here I have another coefficient. It's not equal to this one and this one. The coefficient here I have is this and 0. As a prototype example, so you see what's going on in the general setting. One good property is saved, which means that you have the representation F equals to this. On the other hand, it's not unique. In more advanced properties of frames, we can show that these coefficients have minimal energy, but I mean, I do not enter it now. There are some questions here or comments. Let me see. I think that the set S and T need to be disjoint for this work. Well, yeah, kind of. Yeah, you're right. I mean, it is. I think the way out will be instead of index set. Social, what you said is equivalent to what Alex, what Sheldon mentioned. Because when I take the union, I mean, you product them with 1 and 2, but being disjoint give the same thing. So I've seen in some books they also, what's going on? In some books also they use special notations, like they put a dot here to do precisely what you suggested. It's disjoint union of S and T. But thank you for the comment. You're right. I mean, when I write S union T, there shouldn't be an intersection between them. So to finish, even though I mentioned, let me tell one more time. And among all representations of F as F inner product with Fi times Fi or another alpha I times Fi, if you want to calculate the minimum energy, it means that absolute value of alpha iota squared to be minimum, there is a unique solution, which is this one. I do not enter this. It's a part of course on B-spaces and frames, which is not our goal. I just wanted to give an introduction to these partial frames to say that where they come from and why this representation is important. Next week, I will prove this representation and some elementary properties of partial frames. It will take a few more minutes over time, plus 2 theorems, one from Larsen and the other from Papadakis. And then we will continue our studies of kernels, consequences of Moore theorem and reconstruction problems, some of them. Okay, thank you very much.